All right, so thanks a lot, the organizer, for inviting me here and giving me the nice opportunity to try to summarize the role of simulation in understanding cluster formation in just 20 minutes. I just did a very quick search on ADS. It's like 15,000 papers, you know, with the clusters simulations. I'm pretty sure this catalog is not pure, but it's not complete either. So, I mean, having realized that it's impossible to actually summarize 15,000 papers in just 20 minutes, what I'm going to, I decided to organize this review by first describing which kind of simulations are there in the market, and then essentially describing what I, mainly a simulation user, do find useful in simulations. And I like to think about simulations as something that can provide you information about cluster formation even without data or before getting data. And if you think about that in terms of, in a Bayesian framework, essentially, you can interpret simulation in this sense as your prior information, right? And so what I'm going to discuss is three aspects, and you can see that item 2 and 4 in this list are going to discuss a regime which is essentially prior dominated, where the only information is coming from simulation. Whereas item 3, the comparison between observation and simulation can inform in simulations. And so in this Bayesian framework, that would be a likelihood dominated regime. All right, so different simulations, let me see if I can, okay. Of course, different problems can be described by different simulations. There are two main families of simulations. There are control simulations, in which essentially you are trying to address specific problems, like, for example, what are the orbital properties, what is dynamical friction, which is the some specific physical processes like black hole accretion and feedback, and or what is the the role of cluster mergers by looking at different configurations and different impact factors. And by doing that, you're really trying to address some specific problems by some ad hoc initial conditions. And the other family of simulations is essentially looking at cosmological simulations, in which instead you're evolving cosmic structure from some initial conditions which are set by cosmology. That could be, for example, CMB observation from a vanilla lambda CDM, but could also be some large-scale structure observations, as the latest white cosmological results from dark energy survey, or for latest results from SPT and other cluster cosmology experiments. And in this sense, you can see that the allowed range for cosmology for the low redshift, the large-scale structure, is larger than what we typically think for like astrophysical processes. It's not cosmology. It's not just 0.3, 0.7, 0.7, but you're allowing going from 0.2, 0.4 easily in omega matter, for example. And then after you set initial conditions, essentially GR and cosmology enters only through the descriptions of the Friedman equation in the expansion of the universe, or for the background universe. If your simulated box is large enough, it's very convenient to adopt periodic boundary conditions. And then you evolve these initial conditions up to redshift roughly 100 with perturbation theory. And below redshift 100, you follow gravity and hydrodynamics if there is, by solving the numerical dynamics of the particles, by discretizing essentially your problem in time and either in space. In this case, you have the families of Eulerian codes, or in mass. In this case, you have the family of Lagrangian codes. Now, as we said, we want to describe the dynamics of the particles, and you do that by following gravity through the collision and Boltzmann equation, and hydrodynamics with the Eulerian equations. And in fact, actually, all your terms like cooling and heating from astrophysics, astrophysical processes, as for example supernova heating or AGN heating, enters only at this level of the energy conservation equation. Now I would like to actually make a point about resolution, and it's due to the fact that if you want to resolve let's say a warm intergalactic medium with a temperature of 10 to the 4 Kelvin out to a density of about 10 to the minus 1 centimeter cube particles per centimeter cube, then essentially you want to resolve a gene's mass, which is of the order of 10 to the 7 solar masses, and a gene's length, which is of the order of a kiloparsec. That means essentially, you want your particle resolution and your spatial resolution to be smaller than these numbers here, and current, state-of-the-art high-resolution zoom-in simulations are approaching this regime here. But if you want to go beyond that, modeling the cold intergalactic medium, that requires to go to much higher angular mass resolution and spatial resolution, essentially masses of 10 to the 3 solar masses and resolution of below 10 parsecs, essentially. That means this is essentially unfeasible for cluster physics. Beyond that, you also need to include in your description something, physics like radiative transfer or the description of complex molecular chemistry, which are very complicated. And so essentially, go to the description of something which is beyond the explicit description, something which is beyond the warm intergalactic medium is impossible. And that means essentially you have to adopt some subgrid physics models to describe whatever is happening beyond the resolution of your simulation. And because you're adopting these subgrid physics models, which are described by some parameters, then you need to tune these parameters and to calibrate against some observations, essentially. And so this calibration process, different simulations use different calibration observations, essentially. And so that also differentiate between the different simulations and the prediction of these simulations. And this calibration process is quite expensive. And so typically, you're not even doing a full maximum likelihood to maximize this parameter, but you're doing a by I chi-square, essentially. Now, all these problems here are not there if you're just dealing with the n-body simulations. In this case, you can just feed your simulation with your computer with as many particles as you want. And nowadays, essentially, you can easily treat simulations with trillions of particles. And then the game here is to identify halos and subhalos, and provided that the method in which you identify the halos and subhalos do not affect your results, and provided that the link between the mathematical object, which we call halo and subhalo, and the astrophysical object, which is a cluster and a galaxy, holds on, then you can treat this, you can build your models based on HOD or semi-analytical models. And because these are much effective and much faster than the hydrodynamical, so you can actually, in this case here, do a proper maximization of the parameters in these models here. And then you can populate these halos here and follow the evolution of your structure and understand structure formation. The other possibility is to look at the hydrodynamical simulations instead. There are two ways to do that. One is to look at the large cosmological volumes with a payback, essentially, that you have to balance between volume and resolution. And you can do that, for example, by mixing different volumes and different resolutions. And you want to have the larger volumes in order to follow the evolution of the largest objects. And the advantage of this simulation is that at the same time, in the same simulation, they allow you to follow clusters of very large scales, but also all the low density environment to probe larger cluster centric distances to follow actually properly the environmental dependence of the structure formation. And there are many in the markets here. I just listed a few of the most recent ones. And the other complementary approach to large cosmological volumes is instead to use zoom-in simulations. And in this case, what you do is to take a low-resolution, large simulated box. You identify the halos that you're most interested in, and then you go trace the Lagrangian regions back in time. You populate them with the high-resolution particles, and then you degrade your resolution as you go far away from the central regions in order to still be able to capture the large-scale structure and tidal forces. And then in this way, you're able to do very high resolution simulations of few objects, specific objects, which you have preselected in a sense. And so in this way, you can reach very high resolutions, for example, with like in the example here, the Romulus C simulations or the Hydrangea simulations for few specific objects, essentially. And the drawback of this is essentially that, you have typically a limited number of objects, although there are something like the 300 projects now that are following this way, really hundreds of clusters. But you don't have you know, the largest, you cannot really follow the large environment around the clusters. Now, going back to what simulation can tell you, the first thing, as I was mentioning, is you know, in this kind of regime in which we are likelihood dominated, if you want, is to look for the cosmological dependence. We have only one universe to observe, and so we cannot really predict, you know, understand how clusters evolve in different universes by observations. And as I said, you know, we like to think cosmology is omega matter 0.3, 0.7, 0.7, but because also there is involved this calibration process, which is usually happening at one reference cosmology, I think is always a good, you know, a good behavior to also check whether your results are robust against the cosmology at which your, you know, simulation has been calibrated. And you can do that, for example, by checking that, you know, you can really rescale your calibrations to a reference cosmology. And the obvious thing to check for, you know, for cosmologic dependencies, for example, the halo mass function. And nowadays you can really do that by actually populating, really creating hundreds of simulations at different points in cosmology, like the work done here in the Argon group. But you can also look at how, for example, the internal structure of halos would be affected by cosmology, like in the work in the Ragagnini et al. Work. And if your results are robust enough, you can also check whether, you know, for example, the number of objects identified with above a given velocity dispersion can be used, for example, robustly against different cosmological models. Now, the other thing that only simulations can tell you is the physics dependence. We cannot really play with observations and try to see change the physics there. And but in simulations, yeah, you can actually really look how turning on and off different physical modules affect your results. And for example, you can check for the impact of baryons and see that, you know, for example, if you look at the spin of halos, it's not really affected by the presence of baryons. The dark matter counterparts are close to the hydrodynamical counterparts. But if you look, for example, at sphericity, then there is a tendency that simulation with baryons tend to be more spherical than the one with the dark matter only halos. On the other hand, you can also look, for example, at what happens if you're including different physical properties. And for example, if you're comparing simulation with dark matter only, with simulation in which you are treating the physics of baryons with the supernova, with just supernova feedback, you would see that typically your objects tend to be more massive in the simulation with just supernova feedback, with the full hydrodynamical description. But if you also turn on the AGN feedback, then what happens is that you're effective in removing or suppressing star formation rate and cooling in the center of the halo and ejecting the intracluster part of the intracluster medium, and therefore what you end up is with a halo with a lower mass with respect to its dark matter counterpart. And at the same time, what happens is that you significantly impact the pseudo entropy profiles, which are a very good tracker of the thermodynamical history of the halo, and also redistributing effectively metals in the simulations across the cosmic time, essentially. So changing the different physics affect all different aspects of cluster evolutions, which we can obviously only test in simulations. Another thing you can only test with simulations is the look at the intrinsic properties of clusters by fully exploiting, you know, the 3D or 6-dimensional information that we have in the simulations. And you can look, for example, how the internal structure of halos is changing as a function of the you know, formation time of your objects. What is the alignment between the BCGs and the dark matter halos? You can look also, for example, what is the fraction of substructures in the simulation, and how massive the massive substructures are, or the galaxy-galaxy strong lengthy probability. And you can actually see that for some works, for example, significantly underpredict the number of massive substructures in the simulations, whereas others they tend to find a better good agreement, especially when you're including when you're including the baryons. Whereas if you don't include baryons, the effect is larger. Similar to the 5 minutes left. Wow, never be able to. Similar to the pseudo-entropy profile, also for collisionless particles, you can look at the so-called pseudo-entropy profile, which is defined in this way here, and it's very effective in describing what is the difference in formations, for example, for the intracluster light component and the BCG. And finally, as well, the other obvious thing to look at just in simulation is the evolution of structures. From observation, we compare populations of clusters at different redshifts, and we think that they are the same population evolving in time, looking at the evolutionary tracks. But this is obviously an approximation, and there is scatter, and I am not going to spend much time on this, as this has been already discussed at length yesterday. Now, looking at the comparison with simulations, I'll describe briefly three properties: intracluster medial properties, BCG, and black holes. And a very good advantage in our understanding of simulations has been recently achieved by modern SPH simulations with artificial conduction, which are now allowing to properly describe the cool core and non-cool core properties of clusters. And this also reflects, for example, in the pressure profiles, which we are now able to predict in the median distribution, but also on the intrinsic scatter, which is quite remarkable. And having properties of cluster which are now well described by simulation allow us to be confident in simulation and calibrate, for example, the hydrostatic biases, and be able to therefore inform the other way around observations can be corrected in a sense by robust assumption from simulation on the hydrostatic equilibrium. On the stellar component, as we said, the stellar mass function is quite good reproduced now by most of the hydrodynamical simulation, although there are problems in describing what is the properties of the BCG, and most of the codes are actually finding BCGs which are too massive. And as has been discussed yesterday as well, this can be tracked down to also problems at the high redshift progenitors of the BCG, which seems to actually, on the other hand, lacking of the extreme starburst which are observed in the universe. And this can be seen also in the formation, in the plot, which is describing the formation time as well as the accretion time of the BCG, which essentially, despite all the progresses that we have done so far, there are still in quite good agreement with the Delugia and Bezout early 2007 works. Given these problems in the BCG and proto-BCG evolution, I think it's really crucial to look at the population of satellites and passive and environmental effects. And and essentially this is showing that while at a lower redshift, the different simulations are essentially in quite good agreement in describing the passive fraction. At high redshift, the differences are larger. And it is important, therefore, to actually look at how, for example, environmental effects look at higher redshift, where you can actually start to discriminate between different models here. And finally, black hole properties, looking at the black hole properties. So as you said, some of the results have to be calibrated. For example, the stellar mass, black hole mass in this plot here has been calibrated, but the simulation then can be used to infer actually the robust relation between the mass of the halo and the black hole mass, or the temperature of the halo and the black hole mass, which can be more easily observed and therefore used to infer the black hole mass. And using this simulation, then one can actually try to understand the different accretion mechanism on black holes, and finds out that essentially there are two main channels, and the low redshift regime black hole accretes by merging, whereas in the high redshift regime, they mainly accrete gas. Okay, last two slides. The last part I wanted to mention is the use of simulation to try to forecast simulation observation, and this is particularly helpful in the low signal to noise regime. I think, for example, looking at the intracluster medium of protoclusters, You can actually use the simulation to mock what the observation would look like, for example, for the spider galaxies in X-ray and in SZ. Or you can use simulations to predict what the next generation of hierarchy cluster and protoclusters will look like. And there have been several works now in predicting what is the expected rate of expected detection of clusters and protoclusters, for example, in LSST and HSC survey, or eROSITA, or Euclid and SPT3G. And the bottom line is that, you know, in the next couple of years, I think we are going to witness a situation in which we are going from the current distribution of hierarchy clusters and protoclusters to a qualitative and quantitative different situations. And so I'll finish just with a summary here.
Okay.
Yes, and this is very personal perspective. There is no best simulations, and we cannot actually reproduce all observables. And you know, I have the feeling that whenever I'm talking with observers, they have they are a bit disappointed somehow of the simulations results. But simulations do have predictive power, I mean, although sometimes they can be qualitative rather than quantitative terms. And sometimes, actually often, they actually represent the only source of information. And given the extreme large statistics that we are going to achieve in the next years, I wonder whether the role of cluster simulation is going to change, and if we are going to be a likelihood dominated phase also for the hierarchy part of clusters and protoclusters. So I'm really looking forward to the continuation of this galaxy cluster formation workshop and the next one. And I'll stop here. Thank you.